Mercatio. Mercatio is a company. I say some words about Mercatio in a second. I joined Mercatio 4 years ago, and I'm acting there now as a chief information officer and a lead data scientist. And before that, I have been junior professor at the department here at TU Munich for 7 years. And I run the research group for machine learning and geometric optimization. I have studied mathematics in a formal life, but this is really some time ago. And I still have this Privatdozenten status. This is something like an assistant professor status that allows me to grade my own students and to grade PhD students and to do kind of research. And I have this status here at the TU Munich. Also, I'm not paid anymore for my lectural duties. So everything that we do here is more or less our spare time, but it's always nice to work with students. So that's some words about myself. I mean, some words about Mercatio, not too much because we want to go to a lecture then. Mercatio is actually providing e-procurement solutions for business customers, if you want to frame that in one sentence. And Mercatio is on the market with essentially 2 products. One is the traditional e-commerce merchant, where we are successful on the market now for over 20 years. And you can compare it a little bit with Amazon for Business, but we've been here first. That's the thing. And the second product with which we are on the market is a kind of platform. So we run a platform, an e-platform, where we enable customer and supplier to go into a one-to-one relation and to build their individual e-procurement networks for business customers. So it's a little bit like LinkedIn, but with the ability to trade over the individual connections. Right? This is very short said. And yeah, at Mercatio, we also have a small but nice research group consisting of 2 PhD students and a handful of students that regularly change. Our research here is in the area of machine learning, of course, and information retrieval, also in representational learning. And if time allows, I thought that this morning, if time allows, at the end of the semester, we could give perhaps a small overview of our recent research topics that we have. But it depends on how we proceed here. And with this, I want to give the word to Rayyan and Umer. These are the 2 PhD students at Mercatio in the research group, and they kindly support us, or yeah, in this lecture, this online lecture. And you want to say perhaps a few words to yourself? I don't know who wants to start.
So maybe I can start. So my name is Umer, and I joined, I mean, I'm from Pakistan, and I came to TU Munich in 2015 to do my master's. And then in 2016, I joined Mercatio as a working student. And then I did my internship there and then my thesis there. And then from 2018 onwards, I'm doing my PhD there. So yeah, so it has been a quite a long time with Mercatio. And I hope that we will see you in the tutorials and we will get to know each other better. So that's a brief introduction.
Yeah, so hello, I'm Rayyan, and I guess Umer has like probably given a basic introduction for like both of us, because I have a similar story from Pakistan and joined MSc program at the same time. Joined Mercatio maybe 2 or 3 months before Umer, and did internship, thesis, and now I'm in my 2nd year of PhD. And yeah, so it's my 2nd time taking this course as a tutor. So it's always a nice experience. So I also just like Umer, look forward to you being in tutorials. And I just want to add one small thing, that in the first few weeks, please pay a bit more attention to Moodle, because the general information like the links, etc., that are important for lecture and tutorials, they, I mean, might change. I mean, there is not much chance, but just sort of have a look at the basic information in the Moodle course. So yeah, that's all from my side.
So there will be a short slot now later on where you can say something about the lectures too. So no worries about that. Good. There is something shared on the screen. I see it. No, not yet. I have not started to share the screen. I'll do that later on. Before we start, as I said, I would like to get familiar also for you with these tools that we have in Zoom, and there is a short poll that you can answer here. So if you look at your right hand side, you see the green yes and a red no button, and you see a fast forward and probably also break and applause thing, right? You use these buttons if there are some questions. So I mean, just to see whether you have understood that, could you please use this poll now, and everyone that understood how to use the poll clicks the green one, and everyone who has not understood how it works clicks the red one. All right, okay, I see number 9, 10 for green, 14 for green, 16, 18. Okay, good. No one is doing the joke and saying no, not understood. Okay, 1, I do. Okay. Okay, cool. So it may happen that during the lecture, by and by, I will ask some of these questions like, have you understood this or that? But this will probably not be the question. The question would be more like, do you think that this is correct or this is correct? And then you will have a yes or a no, and so on and so forth. And you can, and every host can clean it, right? Okay.
Yes, yes.
Okay, good. So yes, so I think we are prepared so far, and then let's start. I would like to start with bring you very slowly and into the topic of machine learning, and say a little bit on a very broad perspective how I think. So it's more like an emotional getting in touch with the topic. So in the first few minutes, and I hope now that it works with this screen sharing. So yeah, you should all be able to see the screen. So yeah, so this is myself, Martin, and Umer and Rayyan, you have already known. And you should be able to see the screen, and I should be able to write something. Perfect. Okay, good. Yeah, so as I said, a short thing about this course here. And I like this comic a lot. So what is machine learning? So that's the thing about. Based on your internet history, you might be dumb enough to enjoy extreme sports. Click here to buy a ticket to base jump from the International Space Station. I think internet is trying to kill me. We call it machine learning. I like that a lot. More serious is the following view on machine learning, and that you also might have seen or not. I mean, I guess that, I mean, from these 116 participants that we have now, that there are quite a lot that have already some background in machine learning. So most of these things are probably not new to you, but nevertheless, right, as I said, a kind of emotional getting in touch with the topic. In traditional programming, you had your data and you feed data and a program into your computer, and the computer generates the output. And what machine learning is doing, or can be seen as, is kind of paradigm shift. You have your data and you have your output, and you feed it into a computer, and the computer generates the program. And we could look at this. We could look at this picture for quite some time and see what's the actual point in this, and what is it happening. And if you look at the second part of this slide, what it actually not so less philosophic point of view on that is that, well, actually, I mean, there is a kind of a program framework into this computer, but this program framework allows for a lot of unknown parameters. And what you do with your data and your output is that these parameters adapt over time to your actual problem, right? So that is how you can also see that. There are quite some different views on what machine learning, and I have catched 3 more or less orthogonal views on that topic, and all are correct. So they are all, there's nothing wrong in that, and they're all good. And depending on what problem you have, it's nice to take over one of these views. So Tom Mitchell says that the field of machine learning is concerned with the question of how to construct computer programs that automatically improve with experience. That's a relay to the picture that we just saw. Trevor Hastie said that vast amounts of data are being generated in many fields, and the statistician's job is to make sense of it all, to extract important patterns and trends, and to understand what the data says. We call this learning from data. So that is more a statistical point of view. It's like getting information out of the data. And last thing is, pattern recognition has its origins in engineering, whereas machine learning grew out of computer science. However, these activities can be viewed as 2 facets of the same field. So finding patterns in data is also one thing, and a lot of these things rely to one is one goes in the direction of supervised learning, there's unsupervised learning with these patterns, and so on and so forth. Yeah. So a little bit more concrete, what is machine learning? It consists of, well, actually, one thing is the data modeling. So in practice, this takes a lot of time if you want to make things run. So it's from phenomena to data. I talk about that a little bit later. So it is right. I mean, in practice, you have some natural things going on, and your computer can only digest numbers. So data modeling is somehow from looking what happens around you and mapping that to real numbers that a computer can digest. This is the first step, and it's a very important step. And once you've done that, you use machine learning to identify or let the computer identify phenomena or classify different things that happen out there. You group or cluster phenomena in order to condense information. You can also use them as visualization. You can predict things with machine learning techniques. Or you can also find dependencies between phenomena. And then you see already that the dependencies, that this also goes in the statistical direction. So this is, at a glance, things that you can do with machine learning. Right? What you cannot do is, if the data modeling is wrong, you cannot extract any information. Okay, so it's always the base. Machine learning, I mean, it's somehow funny if you talk about machine learning with people that are a little bit away from engineering or from mathematics, and they sometimes think that you can do miracles with this machine learning, but you cannot do miracles. Right? It's, if your data is good and if you have good data modeling, then you can do cool things. If your data is not good, you cannot foresee anything, right? I mean, if with 2 data samples, you cannot give a good prediction to the future. But yeah, but this is clear for us. So, and the cool thing about good machine learning techniques is that all these identification, classification, group things, that they somehow improve over time. So they improve with experience. The more data you have, the more experience you have, the better your algorithm should be. Yes, and if you look at what machine learning needs as competencies, there is a bigger statistic part, there is the programming part, and there is a mathematics part. And I would like to add here in this mathematics part, in particular, optimization. Because what we will see a lot also in that lecture is that the idea of how we can identify, classify phenomena and so on and so forth, the idea is actually here very quickly. But at the end, what we need to do is we have to make it run on a computer in real time or so, and then we have to use trade-offs between what we actually want to have and what we can do in terms of feasible optimization tools. Yeah. So these are some of the views. Okay, it's not yet time for a break. So let's do a little test. I like the test because it should somehow give you also an idea of what machine learning actually also is in terms of reducing dimensions. And I typically do this test in the audience. I don't know whether it works online. So find this person in the audience. That's the task. And yes, and I think that most of you are able to identify the person, namely it's me. Okay, and now you ask yourself, what's that test? What is it for? And I would like you to reflect a little bit what you have done. So there is this image of myself. It's over 1 year old. It was at the Oktoberfest. That were the good times where the Oktoberfest was still there. And you look at this picture, right? And even if I show you the picture and I turn it off now, you would be able to find me, okay? Because you have this picture, your brain has somehow digested the information of the picture, and now you can map this information to all the other pictures that you see here in the audience. I mean, actually, there are just 3 of us, all others are not seen. And the question is, how is that possible? How can we do that? And surely, I mean, the picture that you have here consists of, I don't know, 1 million pixels or so, even more. And the other picture is also 1 million pixels. And of course, you don't store in your head this 1 million different grayscales or so of your image. But what you do is you have learned to extract features from that image. Only a few of the features. You don't know how. You don't exactly know what. I mean, you're not measuring the eye distance. You're not measuring the length of the big nose. You're not measuring the size of the mouth, right? And store that in centimeters. But you have a very implicit way of storing the information in your head. And you can do that in a very low dimension. It's very robust because I have not the same shirt. It's a different background, and still you are able to recognize me. And this in machine learning, this is also called feature extraction, automatic feature extraction, and it is very robust and very, very important to extract and store information. Yeah. Okay, so these features can be very abstract, but they are still there. Yeah, and there are some methods we will see that extract this kind of information. Good. So that was the questions to think about. So how do we store and extract the pictures information? What are the chosen features that we have? Can we name them? Probably not. Right? It's not this physical meaning of distance between eyes and so on, but they are still there. So they carry the information of the data, and the question is, can we compute them? And yes, there are ways of doing that, and we will strive over them also in this lecture. Yes. So I mean, lots of applications are based on these kinds of things. Like there are lots of applications in speech recognition, text classification, image analysis, and data visualization. What we are planning to do in our lectures is that we, I mean, traditionally when I was at the TU Munich, I did a lot of work with image analysis and computer vision. So this will still be a part here, and also for text classification, because it's getting more and more important also for us at Mercat here. So the examples that you're dealing with in the tutorials, they will hook on text classification and also image analysis tools, applications, sorry. So we will not do anything with speech recognition here in that course. Okay. Oh, I like this. I like this picture a lot for visualization, for data visualization. Can I can make it even bigger. So if you like, if you like whiskey, that's a nice way of visualizing data. Right, so you map somehow the taste of whiskey onto R2 in a two-dimensional map. So this is the data visualization, and it's fun that you can do these things. If time allows, we talk about these techniques too. Right, so there is from smoky to delicate and light to rich, and so on, how these things work. Right, it's important to visually grasp information about the data that you have. So, okay. So what is the outline of the course? We start with a statistical view of how to make decisions from data. So it will be a rather formal approach to the problem. We discuss the curse of dimensionality. So what is the problem in high dimensions? We talk about how to come from phenomena to data. This is what I said at the beginning. That the modeling of real-world phenomena in the real world is really challenging. We start with logistical regression to get a very easy and powerful tool to solve rather the standard problems, to have like one tool where we can start solving problems. Then we talk about principal component analysis. We will spend some time in neural networks. We can talk about linear discriminant analysis. Then we talk about the kernel trick and what kernel PCA is. And finally, we look at support vector machines. So that's the plan. We are rather agile in saying that how far can we go? How far? What's the pace? As I said at the beginning, I have no clue how the pace here is in this online setting. And also since we only start in November, I think that Christmas may become maybe a little bit earlier. Maybe Christmas is earlier to this year and is after the feed-forward neural networks. Yeah, but let's see. I mean, Christmas comes when it comes. Sorry?
Yes, I mean, I also think so. We have to shift a bit. So I just would like to remind you that we are 30 minutes into the lecture, so maybe it's time for a short break.
Yes, exactly. Exactly. Let me finalize that. So there is the linear algebra, statistics, and optimizations are things that you need for this course. I strongly recommend that. I mean, I cannot repeat all basics in linear algebra, statistics, and optimization. Right. This is the thing, because it's a machine learning lecture. So whenever there are things that you should know from your bachelor studies and you have forgot them, please be responsible enough to look them up for yourself. We will support you wherever we can in the tutorials or so if you have questions. But my expectation is that you learn these things on the run, right? If you have, I don't know, forgotten what are the singular values of a matrix, then look it up, because we cannot repeat that here in that course. Good. So that is here the literature. We can put that online later on. If we have some important lectures and papers that will be provided on Moodle. And before we go into the structure of the course, we can make a short break. We can look at the questions that have here, that have raised here, and
okay. So if you guys have basic MATLAB skills like indexing of arrays and matrices and broadcasting and things like that, then there will be, of course, a part of the tutorials that will get easier for you. But still, I would recommend that you start taking like Python tutorials maybe by yourself also. In fact, we also have a small overview of Python and the basic libraries that we will be using as a first tutorial. So I would then suggest you also come to that tutorial so that you know what are we dealing with, and then you guys can look at that further if more training is required. Yeah, and
Okay,
then
I
the
would just
question
like
is
to add
how
something.
advanced should.
If there is a question by Vladimir, and he's saying that maybe we can, me and Rayyan, you and me can speak a bit louder because they cannot hear us properly.
Okay. I hope this is better now.
I think yes, Vladimir says yes.
Okay, cool. So now the question is how advanced should be. Actually, Martin, now actually the questions have now started to come, so it might take more than like 2-3 minutes, but I don't know how we should proceed here.
Okay, so I will try to summarize some questions because they're like on the same path.
Yeah.
So you don't need too much advanced programming language. So, you just need to know basic Python. By basic, I mean you just know how to write a for loop, okay, and how to use some basic functions, and then you can learn the rest as you go. So we do not require any TensorFlow, but I think we use some scikit-learn, and it's very, very, very basic. And I mean the details we will discuss in the tutorial. And the second question was regarding the assignments and the midterm. Assignments we will cover now in the structure of the course. Martin will tell you guys about it, also about the midterm. And one important question is that what about the group work? So in the Moodle you can see that there is assignment group selection. So you can choose. I mean, you can make your groups. So we would like that you do it, I don't know, maybe around 18 November, you should just try to finalize the group so that we hand over you the first assignment. And that would be really good. So assignment can be, the maximum number of people in one group can be 8. Okay, but we try that you have like 5 or 6 is also fine, but it cannot exceed 8. Okay, and that's it. And lecture notes are also uploaded on the Moodle. So when you see it after the lecture, you can see them. The lecture notes are there. Okay, so I think maybe we can then discuss in the next meeting, in the next break, Martin. Yes.
Okay. Yeah. Okay.
Yeah. So you have time to read over the questions, and we can consolidate that just before the end. Okay. So the structure of the course is. So there will be 2 hours of lectures, 2 hours tutorials. All in all, there will be 3 assignments. The coding exercises will be in Python, as already stated, and there will be an examination at the end of the semester. It will be a 90 minutes written examination that will count 2/3 of the overall grade. The assignments will be 1/3 of the overall grade. I mean, we still have not decided whether the examination is on-site or remote, depending on how the situation is. But we are prepared making it remote, a remote exam. So it probably will be a remote exam. So if I have to decide it now, I would say it's a remote exam, but we have not decided it yet. Let's see how the situation evolves. Good. So yes, the first assignment will be announced here on Moodle. First tutorial is this Thursday, same time, 9:45. Have you uploaded a basic Python tutorial on Moodle so that people can have a look at already, and that they can install their the Python tutorial?
So the tutorial is uploaded but hidden from the students, so I will make it public after the lecture.
All right. Okay. Perfect. Thanks to you guys. Okay. Good. Now, so here, this is the contact. If you want to contact us via mail, this is the thing. These are our email addresses, and yes. So, questions. Write your questions in the chat. We will consolidate them and discuss them at the end of this lecture, and see whether there are still some open questions there. Right? Then, I'm very eager now to really go into the details and into the topic. One question was, is it a rather theoretical course or is it a rather practical course? It will be probably mixed. I mean, as I said at the beginning, I studied mathematics, and I'm more at home in the theoretical world. Nevertheless, I try to give you a practical course with where you're able to have different views on different methods, and get let's say an overview of what ideas are behind the different methods that are out there. And this is probably the thing. We will not prove so much of theorems. There will be some smaller proofs in the course, but it will not be a math course. So let's see. I mean, I think for those who had this question at the beginning, after the next 20 minutes, you will have a good idea of how deep it will be theoretically or not. Let's see. Okay, good. So let's start from phenomena to data. This is what we already what I already said. So we have some real-world phenomena, like, for example, business processes. We have a customer that comes onto the platform, that makes the deal with this one, and so on and so forth. So this happens in the real world. And if you want to analyze that, or if you want to cluster or do some funnel analysis or whatever, you have to map these things into a digestible form for a computer. And for us, this is RP. Or if you want to analyze visual objects, you take a picture of a cat, for example, and you have to transfer that into some, vector that can be digested by a computer. Same for documents. Now, if you want to look at that at this issue in a mathematical way, you say that you have actually it's best modeled saying that this is a random variable x, right? And this random variable x goes from some probability space omega to some RP, right? We will not look so much into the detail. For us, the realization of this random variable in RP are the important things. And that can be very trivial with no expert knowledge. For example, if you take the picture of this cat, one way of modeling the data is really that, well, you turn the image into grayscale image, and then you count the number of pixels, and then P is the amount of pixels that you have, and the values here are the grayscales of this pixel values, right? So you will vectorize it. So the first right, the RP consists of here the first column, and then to that column you concatenate the next column and the next column and the next column, and then you have this grayscale. So it's really no expert knowledge or whatsoever. Here you just have the camera as your expert. Things become a little bit more tricky if you have data that is mixed with where you have an image and you have some I can make it a little bit larger here. You have some information here that is a little bit more than text information, and you have a description text, and you then can already see how it makes it that's kind of difficult to really extract here a random variable and turn that into an RP vector. Okay, but this is yeah, this is an art of doing that. Now, if we look at that, we can immediately see from a large perspective what machine learning is doing, namely, why is that not working? Okay, good. I mean, once we've done that, as I said, we can identify, classify, group, cluster, or predict phenomena. We can relate different phenomena, and so on and so forth. And the question that I want to raise here is, where do we need machine learning for? If we have a larger P, so the larger the P, the better. Is that the case? Or can we reduce the P to be rather small? And so for example, I mean, depending of what you want to do with this data, for example, this image data here, if we let the camera decide what the RP is, we have a large P, but we have almost no expert knowledge, right? It's kind of the raw data is coming in, and we are trying to processing the raw data. If there would be an expert, he would be able to reduce that data into saying, okay, so this is a cat, and this cat is red, and we could somehow reduce that. It's actually, I don't want to go so much into the details here. Just saying that, so the more expert knowledge you have, the smaller you can choose the P, and the easier would be the processing of this P, because you have this information retrieval part already summarized in this random variable X, right? So you can put this, you can put expert knowledge in this X, and that reduces the complexity later on. But machine learning is about to shift somehow this expert knowledge that you typically have in designing this random variable X onto a later stage, and to do that automatically. So let's see how this can be here in practice. Okay, so let's look to a very easy example. Decision making on a very easy example. So assume that we have images that we want to analyze, and we have images of two objects, images of apples, and we have images of pears. And here the first step is that we, as I said, want to model this this data here. Then we want to feed that into a classifier, and the classifier should then decide whether or not this this image is an apple or a pear. So that's the simple problem. And if you would have someone, so I mean, just to make it a little bit clearer what I tried to say beforehand, if you have an expert designing this random variable, and the expert labels everything with apple and pear beforehand and says, so this is an apple and this is a pear, and you would directly have this modeling in this data X, there would no machine learning would be needed, right? Because the camera itself would directly say apple or pear, right? And here we want to shift this to a numerical algorithm that does it. So we choose an input data X. For example, here in that case, as I said, as a grayscale image. Okay, so X here is grayscale image vectorized. Right, so it's a large vector, and you have the first column here of the grayscale image between 0 and 225, and you have then the next. Right, I mean, this is just to give you an idea, and not to be afraid of that. So this is how you construct a very, very large vector out of an image. Okay, and this is our input data X. And this lies here in high dimensional space.
Martin, I have a question.
Yes. Yeah, so I mean, for all the other in the audience, we agreed that we agreed upon Umer and Ryan that they are reading the questions, and whenever there is some questions, they feel and consolidate and then ask and interrupt me. So they will speak for you. This is the thing. Okay, Umer, go ahead.
Yeah, or try, at least try. Okay, so you have been saying a lot that this is a grayscale image, but I mean, this is clearly a colored image. So how do we convert grayscale, I mean, from a colored image to a grayscale image?
Well, I mean, you can do that in different ways. So the colored image actually consists of a superposition of 3 colors. There is a green channel, there is a blue channel, and there is a yellow channel. If I get that correctly, and you can.
It's RGB, red, green.
Yes, RGB, for example, and then you can also blow up this image into an R3P and have all these different channels separated, or you can find an average between these channels. That's what you can do to get a grayscale image. Right? Grayscale image is just one way, right? You can also go and go for just the green channel. It's not so much of an importance for what I'm going to tell you if for this classifier thing that I want to look at you. So it's just here one trivial way of getting an RP vector out of a colored image. Okay. So because we don't want to go so much into computer vision.
Yeah, this answers the question. Yes.
Okay, good. And so that's the input, and as an output we have 2 possible outputs, apple or pear. I would say that the apple here is -1 and the pear here is +1. I hope I do it the right way. Otherwise, let's see. Okay, and the aim of this classifier is to learn a real valued function, decision function, that given a realization here x of our input vector, of our input variable, I apply this function to that vector, and it predicts whether it's a -1 or a +1. Okay, so f is a function from RP to R, and it outputs you -1 or +1, and it should be correct in most of the times. So that is the first step. So we are modeling this problem, saying that we have realizations of random variables. So the input random variable is x, and the output variable is y, and we are looking at that in a probability space and saying that we look at the joint probability density function of these 2 variables x and y. Right? While x is very high dimensional in RP, y is only discrete variable, and we have this training data at the beginning, and this training data samples us a joint probability density function of these variables x and y. Okay, and of course, so let's have a look at this probability density function. I mean, of course, this is just a sketch, because the x that we have here, I can only draw it in 1 dimension. Typically, it's of much higher dimension, but you get a little bit I hope you get a little bit an idea of what's going on. So we have samples x and y, and we try to draw them, or we try to sample here this joint probability density function, and from that density function we would like to see what have we learned from that if we look at that. So what have we learned in terms of if we have a new sample of x, let's say this one here, new sample of X is coming. This one. What would you guess, or what would a good decision function output you if this is the input? This is a new X. What Y would you expect? So let's try to do this vote thing. Is it like this here? Voting means Y is 1, and this voting is -1. Do you want to give a vote? So, okay, -1, 14. Yeah. Yeah, the vote, sorry guys, the vote probably not in the chat, but the vote here on this poll, right? This is, you know, I mean, the green button here.
Okay, maybe I can, yeah. If you go click on the participants list, you know, you have the participants, and then there opens a window, and there you have like yes, no, and all these polls options available. You have to click on the participants.
Okay, so right, you see, I mean, we will learn that on our way. But this is for sure. Okay. Okay, because I mean it's good if you participate, but if like 127 people pull the 1 or the -1 into the chat, then you know this is what I mean. Okay, good. So 36 people have participated, 37, and they all vote for 1. I would also have voted for 1 because what you see is that given this sample X, right, so if we have this sample X, and if we look at the conditional probability distribution in that context, we see that it's much more likely, right, to have Y here than it would be to have this Y is -1 here, right? Because the conditional probability distribution would probably look like this here. So the probability distribution of Y given X is 0.5 would probably look like this here and here, right? And so you would vote for 1. Okay, so if you look, so if you see that now, and if you say, oh, conditional probability distribution, and how was it, and so on and so forth, take that home with you as a homework and look it up again to understand what we've done here. Okay, but yeah, intuitively, you would expect a good classifier to choose Y is 1 here. We will look at that example later on, because interestingly enough, you have not taken into account probably, I mean, I suspect that you have not taken into account what happens here if X is larger, if X is at 4 or 5. You're not so much interested in what happens there. You're just looking locally at what this X new is doing. And that's an interesting point of view. We'll come to that later. Okay, good. Then I erase that, because I think there's a comment. So yes, so the task is to find a suitable decision function f that assigns a plausible output to a new input, and this plausible output is now something that we say, okay, what does it mean, plausible? I mean, how do we model that? What is good and what is plausible? So you have to bring that somehow into formulas on the paper, and therefore, what you do in machine learning is you define a loss, and the loss means that the loss is something that like penalizes you if you do it wrongly, and the higher the loss, the less plausible it is what you want to achieve. So mathematically defined, the loss is a non-negative real value measure, right, for the deviation of the output and the decision function. So you have this output y, and you have the real decision, and you have your decision function f. And this is, since y is a random variable, x is a random variable, f is something, right? We don't know yet, but it's also together a random variable. And you want to measure. So this is the loss. The loss is a real random variable, and you go to the expected loss. You look at the expectation value of that function, and say, okay, what f can I have, or how can I find f that somehow minimizes the expectation function, the expectation error here. This is how you can now grasp it, and how you can go and find the best f. Okay, so we want to find the best f, and best always means best with respect to what, with regards to what. And in order to be able to define best, we need to define a loss. One example is, for example, the squared loss. We say, so I have an input x, I have what my function is making out of x, and I have the real value y, so the true random variable here. And I say plausible means that it's good if we minimize the expectation error here of the expectation loss, if this is the loss. There are also others, how we can measure the deviation of output and what the function is doing. For example, why not, right? For example, you can always go for, you say, okay, I take this output y minus f of x, and then I just take the absolute the norm of both of them. Right? There is actually no need here to go for the squared loss. Right? This is also something you can do. Let's see. Yeah, and okay, so yeah, perhaps let's go back here again. So we have the joint distribution of the input and the output, and we have and we want to find a function that somehow best predicts the output given some input, and what best here means needs to be measured somehow, and for that measure we need a loss, and the loss is actually a random variable. Right? The loss is a non-negative real valued function, and if we feed this real valued function with two random variables, it's itself a random variable, and you cannot minimize a random variable, but you can minimize, for example, the expectation value of a loss function, and therefore you go to the expected loss. Why am I saying that? Because it might also make sense to go for the median of this loss function, for example. Right? This would also make sense. You are not. I mean, no one forces you to look at the expected loss, but that's what we do at the beginning. Okay, so it's just one moment of this function. Okay, so let's see, and then there are two ways of or two different ways of approaching that. One is one are the so-called global methods, and the global methods say that, okay, what I start with a class of functions, so I'm not taking any. I'm not looking at the whole universe of functions that is out there, because that would be too large and not feasible. I'm starting with a class of functions, for example, affine functions or squared polynomials or whatever. And out of that class of function, I want to find the best one that minimizes the expectation prediction error. That is one way of approaching that. And there are local methods. let's say, okay, I'm not really interested in a closed form formula of this function f. I'm just looking at what is the best local value of a decision for a given realization of x. So that means I'm just looking at what is the best prediction that we have if we minimize the expectation of this conditional distribution here. And actually, I mean, I bet that most of you that voted for the y is equal to 1, that they use these local methods intuitively. Okay, so let's look in this typical example how that's more concrete, how that looks like in that example. So if we look at if we define or predefine a class of function f that is described by finitely many parameters, then the best decision function is given by f theta, and theta is the minimum of this cost function here. So for example, yeah, right, I mean, I'm not getting too concrete here with this, not yet too concrete with this function class. I just say that all the functions that we are considering can be parameterized by a set of parameters, and the set of parameters is theta. Right, into that framework are, for example, all affine functions. Right? If you want to have it more concrete, look at affine functions here. And so we want to find the best parameter set that minimizes the expectation of this function here. But of course, right, I mean, since we do not know the distribution of our y and x typically, we don't know it. We need some samples to estimate it. We go from this expectation to the mean, right? So we are estimating our expectation prediction error via samples of the distribution. And from the theoretical expectation value, we go to the mean here, and we just plug in the samples that we have. Right? And so here you need this training set yi xi, and you form this expectation error, and then you have this number, and you want to minimize now this function with respect to theta. So we find an optimal global decision function based on the samples. So once we have this theta here, we say, okay, we have then found our decision function. Right?
Okay, so Martin, I have a question.
Yes.
So you said that we can approximate this expectation with this mean over the samples, right? So
Yes.
are there any guarantees? I mean, what should be the reasonable number of n? Or
Here,
formula hold for any n?
you mean this big N?
Yeah, the number of samples.
Yes. Well, I mean, this is that's a good question. I mean, it depends on your problem. Of course, you want to have. I mean, the larger N, the more you approach the true expectation here, right? But of course, large N is expensive, right? And if the N is too small, you will come to the problem of just finding the wrong theta that does not hold for the whole distribution of y and x. So it's what is called overfitting. I can talk about overfitting next. I will talk about overfitting in the future, right? But yes, of course. I mean, if you want to find your theta and you only have 2 data points, then this will not be a very robust. This will probably not be a very robust classifier. If you want to train 100, if you need 100,000 samples, that's probably too much. And there is a relation between the numbers of unknown parameters that you have and the numbers of samples n that you need. So, but these are already the good questions. Okay. So yeah, I mean, even more concrete in that example, if we let's go for linear regression. Linear regression here in that setting is probably not. You would probably not do that in practice with linear regression, but we can do it as a toy example to understand what's going on here and really make it now really precise. So if we have linear regression, we have like two sets of parameters. There is the alpha that is in R, right? Alpha is real and beta is in RP. So beta has as many unknown components as our input vector P, as our input vector X. And we go for a fine decision function that looks like that. Okay, so we have here alpha, like a threshold, and then a linear combination of our features X. So I define the function class that we are searching for as the set of affine functions. Okay, and then that means the classifier can only output me the best affine function for the problem. And how can I guess this best affine function? Well, I decided to use as a loss function. I decided to use the squared error. Right, this is also what I decided. Right, this is not from the problem itself, but this is my decision, my choice. I choose linear functions. Any other functions are also possible. I chose the squared loss. Any other loss would also be fine, but this is what I decide. And then I want to minimize this function here so that it best fits to the training set. Right, and then I said, okay, so this alpha hat and beta hat defines me the best linear decision function, the best affine decision function for my problem. And just a remark here, in practice, you would not do it with that linear function. You would use logistic regression, but it serves here as a toy example to make the things clearer what's happening here. And right, and you can also draw that in 2D, where you have now this distribution of X and Y in a kind of other representation. So it's the same, actually the same representation that it's the same samples of than before, but X can now be two-dimensional. So we have one dimension more to visualize, and the dimension of X of Y plus one or minus one is now encoded in colors. Okay, so that's this picture here, and yes, and well, and when you learn your decision function, it's the function that says, okay, so if you are here on one side, you are positive, you go for +1, and if it's negative, you go for -1. Yeah, so this concept of global methods will also be a part of neural networks, for example. They all also go mostly for global decision functions. So that was one sketch in this global method direction. And if we go to the local methods, what we want to do is we want to solve, as I said, so the expectation. So we have the loss function of Y and C, and we want to find the best value that minimizes here the condition expectation. And if we write that down, we see, okay, the expectation value of so we have this loss function, as we said, was the square log expectation of Y minus C squared. We use here the linearity of the expectation value. And we see that, well, I mean, the value that minimizes that function, I mean, it's just a square function. This here is the constant term with respect, to C. And we see that the minimal value here comes exactly if the C hat is the expectation of Y given X. So exactly the best prediction of Y for a given realization is the conditional mean if best is measured with respect to the square. And I'm handing over to Umer, who has collected some questions.
No. So the question is, what is C?
C is the value. I mean, it's the question. C hat, right? I mean, C hat is the value that minimizes the expectation here under the conditional distribution. So it's exactly if we come back to this image, right? You remember that you saw this was 1. Oh, sorry. This is 1. This is -1. Remember? And and if you restrict yourself to one realization, X, you have a conditional distribution of Y. Right? You have this conditional distribution of Y, and this conditional distribution of Y given X looks like -1, 1, and has here some probability distributions here. Okay, and if we and now, so right, this is the probability of Y given X, and we also have the loss here of this Y. So there is a function that is applied to that random variable Y, and we want to find a C that minimizes the loss here. And the loss C hat is exactly the expectation, is the expectation here of this distribution. Right? In that case, if this is, I don't know, if this is 0.1 and this is 0.9, right? C hat would be 0.9 times -1 plus 0.9 times 1. Okay, in that case. Because this is the number that minimizes the expected squared loss.
Yeah, so in other words, if you want, I mean, the best prediction with respect to the square loss would be the mean, the conditional mean, right?
The?
So the best prediction
Yeah.
with respect to the square loss would be the conditional mean. If the C is,
Yes.
yeah.
Yes. And this is very typical. I mean, but this only holds true if we look at the squared loss, right? Because only if we have the squared loss, we can do this computation here, right? This is why the squared loss is important here. If we have another loss, for example, the absolute value, this is different, right? If we look at if we want to minimize, let's see. So if we want to minimize, this thing here, C hat, and we have argmin, C in R, expectation, I'm not giving here this conditional thing here because it takes too much time, of the absolute value Y minus C, right? Then it's not so easy, because then we cannot use the linearity of the expectation value. And then it's some work, more work, to show that in this case, C hat is an optimal solution is actually the median of this distribution of y given x. I'm not going to show that here, but I'm just so my point here is that if you want to draw decisions from this data, you have to define a loss function, because the problem itself will not give you the loss function typically, and you will have to decide with this loss function whether you're going for local or global methods. And if you go for global methods, the class of functions that you're choosing is also not defined by nature. It's also you that have to define that. And if you go for local methods, you see that the loss function here plays an important role. So the concrete example with these images, so let's look at that again. So estimation of the condition, estimate. So we need to estimate the conditional mean. I mean, this here is still theoretic because we do not have the distribution of y and x. So we cannot compute the expectation value. We have to estimate that. And the question is, how can we estimate it? And we estimate it the way you have done that beforehand in this toy example. You have estimated it and you said, okay, so that should be you know, here around 1. And what you do is you look at the training samples. So you have all this training sample x1 to xn, and you look at a neighboring set. So you choose your realizations that you have. X, so this is your realization X. You look at all samples that are in a neighborhood of X. So you consider into your decision, you consider perhaps this one, this sample, and all these samples here, right? This is what you take into your account for doing the decision, and you have to enrich somehow the neighborhood so that it makes sense, that it's not empty. Right, so you choose the training samples, you choose a neighboring sample set, and the estimation of this conditional mean is then you average over all the yi in that neighborhood. Right, so you look at what x are in my neighborhood, right? For which y do they vote, and then you take the average of what they voted for. So this is a very standard local method. So it's called also the k nearest neighbor method. So if nkx is the set of indices of the k nearest training samples of x here, we have a local decision function based on training samples. This is this one here, and if I look at the realization, so it's the same again with a two-dimensional representation of x. We look at what are the neighbors of x, what are they voting for, and depending on what the majority vote is, we also vote for x to be there. So it's rather trivial, right? So in an example, a toy example, or not in an example here for if we want to recognize digits, so we have training set. So this is our training set, and the training set consists of 2s and 3s, or apples and pears. Should have been better to make it with apples and pears, but we did it with 2s and 3s. And there is a new image coming in, and the question is that now, is it a 2 or is it a 3? And what should our algorithm vote for, and how can we do that? Okay, so what we do is we compare this, our p vector, with all other vectors that are in our training data set. We look at what are the 7, I just here chose k equals to 7, what are the 7 nearest neighbors. I measure the distance with Euclidean distance. and say, okay, so I found out, so the Euclidean distance from this vector to all the other vectors, the 7 nearest one are this one here, these ones, you know, all that are marked in green, that are the 7 nearest neighbors. I don't care about the rest. And these neighbors here vote for 1, 2, 3, 4 times they vote for the image being a 2, and 3 times they vote for the image being a 3. I modeled here being a 3, that is y is 1, and here being a 2 means y is -1. And so the best prediction here is -1/7. And so your decision would be the sign of -1/7, and this is -1. Okay. So very easy way of driving decisions here. Just look what your nearest neighbors are, and of course here you come in another problem. You have to define what nearest means. Right? If you are in 1 dimension, that's easy. If you are in 2 dimensions, that already starts not to be trivial anymore. And if you are in RP, the question is, how do you measure nearest neighbors? Which norm are you using? How do you measure the distance in RP in order to define what nearest neighbors are? And all these things are ingredients that will then concretize your algorithm one day. Okay. So I think we should spend some time for questions here. Time is running. Okay, I see.
Yeah, so so there were some questions earlier, but they were regarding the administrative stuff. So there are not any technical questions outstanding.
Okay, good. But well, I mean, you should answer this administrative stuff anyway, right? So then I will close here because the time is up. So let's summarize, right? I mean, I would only like to give you like a glance into the 2 directions of local decision making and global decision making. I want to give you so the message is that in order to see what is a good decision function, you need to define a loss, and only with a loss it makes sense to talk about a good decision function or not, because otherwise it cannot be mathematically digested, right? Then, if you have this loss, the loss is actually something that is defined on the joint distribution of x and y, right? And if you want to minimize it, you want to look at a momentum of this random variable. So you want to find an expectation value probably that and a function that minimizes that expectation of the loss. And this is the very rough way of how most of or a lot of machine learning techniques work. And we have exemplified it with 2 very trivial examples, just to go the whole way through one time. And we will repeat that again with other methods. Yes, so that was it from my side. Now, thanks for that, and also thanks for your patience, and thanks for your not being too harsh with the situation. So we will all grow into that. We will all become better. Thanks for your time. Hope to see you again next week. Same place, same time. And then I give over to Umer and Rayyan to answer the administrative questions. Thanks.
Thanks, Martin. So there are actually two questions. One is that regarding the sharing of the course slides. So we will share the course slides on the Moodle. So just stay tuned. And second thing is that assignments are only possible in groups. So you cannot uh, submit assignments as a single person. Okay. So assignments are only possible in groups. So it helps you also, I think, in learning how to work in teams. Okay, so and the third question is, I mean, it's not a question, but it's a remark from my side. So we have a discussion forum at Moodle. Please make use of that because I mean there would be many questions which your colleagues can answer easily, and or if nobody answers, then me or Ryan, we will see it and we will answer it. So make use of that discussion forum at Moodle and post your questions there, and any problems you're experiencing, just post them there. We will also try to record the tutorials, and hopefully we will also think of where to upload them so that you can also view them, right? So don't worry about that. So the group should be maximum 8. And regarding the exam, we have not decided yet how it would be conducted. Okay. Yeah, that's it.
Okay. Thanks.
Yeah.
Thanks,
So
Umer.
there
Thanks,
is
Ryan.
a question whether the group partners can change over time. So yeah, about that, I guess it depends. Like it changes from assignment to assignment. So we have like, as Martin mentioned, okay, yeah. So we have multiple assignments, and you can choose different members
Yeah, so I
in
mean,
each.
ideally the group size should be like 5, right? This is what it used to be, but since the number of people in the course are increasing, so we have to also allow for some bigger group sizes. But the ideal size would be like 5, 6 people. Yeah, I mean, and the minimum should be around 3. Okay, so I'm now stopping the recording and let's hear the funny voice.